Okay, so we'll just resume the same topic, vector algebra, and we have covered so far the addition of vectors. Okay, addition of vectors followed by addition of vectors in terms of their components. Okay, so the pretty much four properties here, they're listed, four properties of vector addition, which we derived from vectors in dimensions 1 to 3, right? Dimension 1 being just numbers, and then on the plane and in space, okay? And then what we did, we are started to talk about vectors represented by components, right? And which is here. And then there's the components and what happens to the components when we add those vectors. And the answer is very simple. In dimension 1, 2, and 3, you just add components to components, x's with x's, y's with y's, and so on. Okay. So, and then we extrapolate that idea of how to add vectors. We extrapolate them into n-dimensional spaces. Okay, why does it work and what is the point? Once again, remember, our n-dimensional spaces are made of a lot of low-dimensional spaces, and so when, for example, you carry out addition of vectors in n-dimensional space, you only have two vectors, and which means that they are contained in, let's say, those two vectors. They're contained in some two-dimensional space, and so addition matches. Addition in n-dimensional spaces matches to addition of vectors in any lower dimensional space contained in that space. Okay, so all 1, 2, 3-dimensional spaces inside of that n-dimensional space will have the same addition as before. This addition that we talked about, that we can actually visualize. Okay, so that works out pretty well. Addition is really simple. The second operation is a scalar multiplication. Okay, and then it has one property, pretty much one we care about right now, or rather it's a property, that standalone property that is entirely about scalar multiplication and not without addition involved. Okay, so that's the associativity property of scalar multiplication right there. So you see on the left you either multiply by b and then by a, or you first take care of those two numbers, multiply them together, and then you have your same result. So that's illustrated right here. So multiplying by 2, then by the result multiplied by 3, that's on the left, and then you can also just multiply 2 by 3, get 6, and you have your 6 times repeated vector on the right. Okay, so that's the explanation of why that associativity works. In lower dimension, then we expand it to n-dimensional spaces in the same manner. It's even easier than addition because scalar multiplication is one-dimensional, so it's all along a straight line so far. There is one more property. It's called the unit element, or unit element. It's very simple. So 1, what happens if you multiply a vector by 1? Well, of course, what do you get? You get the same vector, right? So multiplication is component-wise, and so every component is multiplied by 1, so no change. So some of the properties reappear that we know from algebra of numbers reappear for the algebra of vectors. Okay, so not a lot to illustrate as far as the scale multiplication is concerned, but once we move on to those mixed operations, so we have two algebraic operations just like with numbers. Okay, additions, vector addition, scale multiplication. So first of all, we have two entities of two different nature, vectors in numbers. Okay. And then they have separately operations, addition of vectors only, and then numbers have addition and multiplication. Okay, so then and so far we had 6 properties already. We already have 6 properties, And then now there are more properties, and that is when addition and multiplication is mixed up. Okay, so the property is called what? So combined properties of addition and multiplication. Well, what do you remember about combined properties of addition and multiplication for numbers?
The order in which to do them?
Yeah, there's a name for it.
Order of operations? Is that what you mean?
No, how do you expand? Expand. So you add then multiply. What is the alternative? Add then multiply, or multiply. That's right. Multiply twice and then add.
Oh, foiling.
Well, no, not foiling. It requires 2 and 2, so it's slightly more complicated. It's simpler one, and the word is distributive property. TBT. So a x plus y. Let's say x plus y. This vector is ax plus ay. So the property certainly looks like the distributive property for numbers, but this time we're talking about vectors and numbers. So x and y, once again, I'm using capitals for vectors or points, and I use lowercase for numbers. So as you can see, they're combined together. Vector addition inside the parentheses, then scalar multiplication by a, and then on the right I have 2 scalar multiplications added together. Okay? So straight forward borrowing of the property from the from numbers. Let's illustrate it. I actually have this. Just to remind you that this is this was the illustration of associativity. This is an illustration of associativity, and we also have commutativity. But now let's have here somewhere here's this distributive property. Okay. Okay. So let's see what's happening here. 2 vectors to begin with, and then I choose the multiple c to be 2. Okay. So I'm talking about 2a plus b. Those 2 vectors a plus b added all over there, and then remember every identity that we have in those properties, there is a left-hand side, there is a right-hand side. Starting with the same 2 vectors in the same number, we have 2 paths to follow, and then what the property says, it is the same. Okay, so if we take the upper path, so what's happening for the first step. What am I doing? A plus b, the blue vector is a plus b, and then look at it, what happens next, I multiply by 2. Okay, so there you go. Now if I took the lower route, I first multiply the 2 vectors by 2, right, though you can see those, and then I add them together in the next picture on the right. Okay, and then we just need to demonstrate that it's the same thing, and the last 2 pictures are supposed to suggest that it is indeed the case. So as you can see, what we're talking about here is simply that little parallelogram over there on the upper second top is kind of repeated 4 times, right? You see it? That the big parallelogram on the top bottom right, what is it? It's made of 4 parallelograms like this. Okay, so and that sort of suggests why it works the same the way it does. Okay, so this would be a parallelogram like this, where you can see it. And well, just once again to demonstrate that this is not made. This is indeed an actual spreadsheet. So we certainly can recompute all of this. And as you can see, things are changing, but remain the same. So the property remains for any whatever vector you choose. So once again, upper path is the left-hand side, where here we are. The left-hand side, this is the left-hand side, the upper path, upper, and this is lower. First adding, then multiplying, or first multiplying twice, and then adding. So once again, here it is. Here they are. Okay? All right. So that the properties that we're going to be freely using. but that they start to accumulate a little bit. Well, the tricky part is, however, that so this is about addition of vectors, multiplication of numbers, right? No, addition of vectors and multiplication of vectors by numbers, scalar multiplication, right? So once again, so a vector addition appears twice, this one and that one, and then elsewhere we have scalar multiplication here, here, and here, right? Scalar multiplication. But there is one more operation that's missing that we did not address.
Vector multiplication?
No, there is no vector multiplication. It is strange, but we don't multiply vectors. When we will, soon we will multiply vectors. We'll call it more and more geometry than algebra. So we're doing algebra right now. So which means that you add two vectors, you get a vector. You get two numbers, you two numbers. There are no number addition here. So here's what if I write the same distributive property, but for addition of numbers. A plus b x is equal to still ax plus bx. So it's still distributive property, but it is about other operations. So I have now scalar multiplication again over here and over there. And I still have my vector addition here, okay? But this one, that's what has changed, is that this is number addition. Okay, so that is called, so this is distributive property, not the same, but not the same as the first one. So that actually calls for a name. It's called distributive property 1 and 2. Okay, so I actually did not pay attention, but if I have I don't think I have another distributive property. I'm supposed to have a different distributive property here to illustrate the other one because it's different, but I guess it's not really that complicated. So if we look at this picture again, so it's one vector. So this is one-dimensional situation. So there's really not a lot to illustrate here. It is like this. A vector x, and then I could multiply it by 2, and I could multiply it by 3, and then I could add them together, giving me 5. Well, kind of obvious that what happens is I could jump right there rather than adding these two together, 2 and 3. I could just add 2 to 3, and then have 5x. So it's very predictable, and so it's much less usable property, I suppose. Okay. Okay. So then we have, to my count, we have 8 properties. Okay, so I have them here, so I don't want to list them for you, but let me just say that we have then commutativity of addition, associativity of addition, the zero vector, special zero vector, remember that's the property of the zero vector, the inverse, so x plus negative x is 0 for a special vector negative x. Then I have associativity of scalar multiplication, and 1 by x times x, I started with that, and then I have 2 distributive property of vector addition. Okay, so 8. Whenever you have algebra that satisfies those 8 properties, it's called a vector space. Okay, so let me maybe number them so it would be clear. So it's this is 8, 7, 6. I hope I didn't miss any. 5. Yeah, 5, 8, 7, 6, 5. Here, commutativity is 1. Okay, it's not the right one. Okay, and well, commutativity 1 and associativity 2, 0 and 3 and 4. Okay, 8 properties. So the point is that you can always go back to, with these properties, instead you can always go to components and carry out these operations component-wise, and these properties will come up there very easily. So it's not really something that you need to remember. It is just it gives you the idea that you can do algebra with vectors just as in the same manner as you do algebra with numbers. Okay, so you just have to be careful every time you do it. Is there a property that allows me to do it? Okay, and so most of the time, pretty much at some point you'll be doing it automatically. In fact, the FOIL was brought up. Is there a FOIL property for vectors? Anyone? FOIL? FOIL, A, B, let me use X and Y. So X plus, no, A plus B numbers, A plus B numbers multiplied by X plus Y vectors. So what is it supposed to be equal to? Well, as you think, if you want a FOIL, then it will be, I forgot what it stands for. F, what does F say?
First, outer, inner.
First, so AX, outer is AY, right? Inside BX, and two last ones, BY, right? Okay, so is it true?
Yeah.
I don't see why not.
Yeah, because you can just, well, yeah, because you can just treat the A plus B as one term.
That's right. You distribute A plus B as a one term, and then you have right. So I'm using distributive property 1. So in other words, number 7, property number 7, it will be A plus BX plus A plus BY. Okay, and then what do I do next?
Just distribute.
Which is property number 8. Okay, property number 8 give me that. Okay, so it's just FOIL is you can use FOIL on one hand. FOIL follows from these two properties. On the other hand, FOIL contains those two properties. So you can say you can replace 7 and 8 with FOIL, just as well, if you prefer.
Well, FOIL's normally with, like, for algebra, it's like a variable and a number inside the parentheses, right? So would this work in terms of, like, because it's going to be a little different because you're going to have to multiply two vectors. If you had, like, a vector.
No, right. So you have to keep track of things, of what you allowed and not allowed to do. So that is actually a bigger deal than algebra. Algebra works out just about every time as long as you keep track of those things that are combined together. So you don't try to multiply two vectors, for example, or you don't. The worst thing would be probably to try to add a vector to a number. That would be really bad. So as long as you avoid all of these things, then you should be fine with your intuition of algebra that you have with numbers. So as long as you know that vectors are not numbers and their operations are only either between numbers or between vectors, or the only operation that otherwise is allowed is you can multiply a vector by a number. Okay, so if you keep track of those, then the rest of the algebra, these simplifications are all work out. Well, one thing, so for example, you're not going to try to divide a vector by vector because there is no vector multiplication to begin with. But can you divide a vector by a number? Yeah, you just multiply by the reciprocal. So that algebra of numbers is still all there. Okay. Okay. So components. Let me once again make that point about our notation, which I've been using. The notation I have been using was the row notation for vectors. So say 2, 3, 1, 7 plus 1, 0, negative 1, 2. I add them together vertically getting a new vector 3, 3, vertically and horizontally, 0, 0, and 9. Okay, but it is identical, or rather equivalent rather than identical, to the notation that is a column. So it will be 2, 3, 1, 7 plus 1, 0, negative 1, 2. And I carry out the same operation. Instead of going vertical, I now am going horizontally. So it's going to be once again 3, 3, 0, 9. Okay, same with scalar multiplication. So say I have 5 multiplied by 2, 3, 1, 7. I have multiplied one at a time, so I have 10, 15, 5, and 35. Okay? So, so the difference is, and right now doesn't matter a lot. They're totally equivalent. Just keep in mind that the second one is more preferable. We just use the first one in order to keep things more compact. But we do prefer to think of vectors as columns rather than rows. It will be more important shortly. In fact, remember, I think I did explain why it was the case. Remember when we very early started with a linear system of linear equations, and we represented it as a matrix, vector, vector. Those vectors were definitely columns, right? So though we derived those columns from those equations written like this. So equations written like that, and then this is a column, that is a column, and then what's left is a matrix pretty much. So that's why a column notation is ultimately is what's happening, and the row notation is just its abbreviation. Okay. Okay. So well, I guess one more. I have a picture here, just maybe for to illustrate it once again. Okay, I'm going away from this. Come on. Open with. Choose. Paint. Yes. Okay. Okay, so it was meant just to illustrate the component idea of vectors one more time. So it's not quite very high definition, but you can see how I have vector A over there, and it is how I understand it, represented by an arrow. Then I look at it as if it is a diagonal of a box. Okay, a box that lies naturally horizontally on the xy axis, and then vertically along the z axis, and then I just look at the dimensions of this box. Oh, and then you can see them in the second picture. It was how much I progress in the vertical, horizontal, and vertical, horizontal x, horizontal y, and vertical z directions. And those are, remember, those vectors I, j, and k. And I just look how many of those I have present. So you can actually see over there blue I vector over there go along the x-axis, j green one along the y-axis, and purple along the z-axis. And then whatever vector A is given, I could express it. Last time I did it in dimension 2, but you can see that what's happening here, and I did not write it out, but you can see that what's actually happening is A is equal to 2I plus 4j plus k. Okay, so that is the decomposition of a vector into its components in terms of the basic vectors. So the basic vectors correspond to, for each axis, it is the vector of length 1 pointing in that direction. So in other words, I is equal to 0, 1. I'm sorry, I is equal to 1, 0, 0. J is equal to 0, 1, 0. And k is equal to 0, 0, 1. Okay, so and as you can see, what we're talking about is a combination. The decomposition is about very nice usage of what we just been talking about, vector addition and scalar multiplication. So I take my vector I, so two basic vectors, and everything in three-dimensional space is built of those three vectors. So I take vector I multiplied by 2, which gives me 2, 0, 0. I take j multiplied by 4, which gives me 0, 4, 0. And then I take k, not multiplying by anything, it is 0, 0, 1. And then I add them together, which gives me my vector a, which is 2, 4, 1. Okay? So that is the meaning of those numbers in the components 2, 4, 1. They are, these 2, 4, 1 numbers are simply, they are simply the, these are the numbers. And here 1 as well. Okay, so that's the meaning of the components. So the decomposition is very simple as we will look at it, but really it does not have to be this way necessarily. The Cartesian system is not always given, or rather what I'm saying is it's not given forever. You might come into this, especially in high dimensions. You already have a Cartesian system provided, but you might choose another one. So here I have an example just to maybe suggest what I'm talking about is this. Okay, so a very simple physics problem about motion of an object on an incline, and then there are no axes to be seen here. So what then you certainly could speak in terms of vertical and horizontal motion as always, but actually since your motion is restricted to the incline, so why would you choose the horizontal direction and vertical when the motion is actually one-dimensional? Why would you choose your coordinates this way as always, even though the gravity obviously moving down along the y-axis, but really your motion is entirely along the incline. So what I'm suggesting on the right, this might be a better choice of coordinates, right? So that certainly in science is done a lot of time. So you see what that picture on the right represents. So you can choose I and j, I along the slope and j perpendicular to the slope. Okay, so then your motion will be very simple. It will be entirely in terms of that vector I. So if I choose to call this vector I over here, this vector I, then all my motion will be one dimension. Okay. All you need to just figure out what the gravity is, okay, and that we'll look into that soon enough. Like I said, so I want to talk about my motion one-dimensional, but on the other hand, my vector of gravity, which is this, pointing in the wrong direction. So what do I do with it? What is the force acting on the
Gravity.
gravity force? Yes, but it's pointing down.
You also have like force of the ramp pushing back, and like so you can make like a right triangle out of that.
You could, but this is if that's what you're talking about.
Yeah.
So as you can see, there are two components of the vector g. One is parallel, and this one is parallel, and the other perpendicular to the surface. We don't care about the one perpendicular to the surface because it's balanced with the resistance of the surface, right? So that is cancels out. It doesn't make any difference. What matters is the components that actually is going along the slope, and that is the one that will be pushing the object. So this is the important part, right? Of the gravity. So once again, this is my gravity. Okay, and then, but actually what matters is this one, the only that thing that matters. Okay, so that way we're going through choosing a good coordinate system, and then it's called a projection, choosing the in addition to finding the component of all the vectors that are relevant to our coordinate system. So if we want to do only motion along the vector I, then I don't need a vector part of the component of vector g that is perpendicular to it because it doesn't contribute anything. Okay, so just to give you an example, we'll do a projection shortly, but I want to give you one more example, which is not if you're not into physics, then maybe this might be more, might speak more to you. So pictures are actually very similar, but what I'm trying to say here is that, so this is not about physics anymore, and what it's about actually is well, say the x-coordinate is stocks and the y-coordinate is bonds, and maybe you're following the rule of your portfolio that you should supposed to have twice as much bonds as stocks, or vice versa, whatever. So which means that green line, gray line, is in fact the perfect portfolios are along that line, right? So when the proportion of stocks to bonds is 2, okay? Okay, so that's the device, and then suppose that dot over there is your real portfolio. Okay, then you can actually ask yourself to how well am I following the advice of somebody, you may be a financial advisor, and you want to know how much you can actually see that on the right it shows the purple vector shows how well you follow the advice, and the blue one indicates how far you deviate from the advice, right? So you're supposed to be on that line, your portfolio, that dot, 2 numbers, so it could be 100, right? But if it's just 2, then it lies on this line, it's supposed to, and yours aren't. So how do you measure your deviation? And that's how you decompose the vector into one vector along that line, and the other one perpendicular to it. And the perpendicular one is the deviation. Well, what remains is pretty much just to actually say in numbers how far you are. You can just take that distance. You can take that distance, and the length of that blue vector will tell you the deviation from the ideal. Okay, so that's that, and that is the next topic, is the length of vectors. Okay, it's once again just like with a lot of other things, it's entirely reduced to the problem of distances between points. If you look at that blue vector, what is the length of a vector? Well, it's simply the distance between the beginning and the ending of the 2 points, right? So there's nothing tricky about that. Okay, so lengths of vectors. So once again, we start in the lower dimension. We are thinking physically or about physical space, how we measure distances or magnitudes. That's, by the way, another word to sort of separate yourself from geometry of distances. That's what the length is, and you speak of the magnitude of a vector, but it certainly is the same. So this is the definition. PQ in lower dimension, that is OP. This is the notation. 2 vertical lines. It is defined by simply the distance between O and P. Well, it looks kind of odd, but so this is the familiar, right? This is the distance. This is the distance from O to P. That's the old idea of distances between points. And now the new idea that we're introducing is this, and this is the length or the magnitude of vector OP. Okay? So since points aren't numbers, points aren't vectors, so you don't want to confuse these two. Sometimes you speak of distances between points, sometimes you speak of magnitudes of vectors. We'll just stick with one or the other, so we know what we're talking about. Okay, so that's the new notation. 2 vertical bars, also known as the length, magnitude, norm. There are several words apply to it. Okay, so properties. Properties, when you define it this way, then certainly properties of the magnitudes will be very much related or similar to the properties of the distances. So remember those 3 properties of distances? we start with distances. And then I will have properties of vector of magnitudes. So remember, what's the simplest property of distances? If you remember, or any, we had 3. Remember any of these? What do we know about distances?
You can add them.
Well, when you add them, what happens? Say AB plus BC. What happens?
ABC.
What's ABC?
A to C.
AC, okay, and? What's missing?
B.
No. With the in between.
Equals.
What? No.
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 Oh, greater than?
Right.
Triangle equality.
That is the triangle inequality, right?
I mean, like it's positive, right? Like a magnitude is positive. Or
Uh,
the distance is positive.
Yeah, the magnitude is the distance is positive, so AB is always larger than or equal to 0, and AB is equal to 0 only if A is equal to B. Okay, so that's the first property. And the second property, what? AB is equal to BA. Okay. So from A to B or B to A, same thing. Okay, so let's try to understand what it tells us about properties of magnitudes. So number 1, certainly it's gonna be so property number 1. We're gonna say that the magnitude of a vector. Let me put x here for a vector, and it's always larger than or equal to 0. Okay, and it is equal to 0 only when? What?
The 0 vector?
The 0 vector, that's right. So x is equal to 0 is the only vector with magnitude 0. That makes sense, right? Okay, number 2 is, well, how will you express number 2? So you see what I'm trying to do here. I'm trying to express these properties for vectors not in terms of beginning and end points, even though that's how I define the magnitude, but rather just with a single letter. So vector x, suppose, and so as you can see, it's x, magnitude of x larger than or equal to 0. Okay, so A, B, B, A, how do you express it in terms of vectors?
X.
Okay, yeah, what about?
Just X.
No. What's the relation between A, B, and B, A?
Negative x?
Negative x, right. Okay, so a negative x, remember, it reverses the direction, so that's exactly what A, B, B, A is. And finally is the triangle inequality. Triangle inequality, so let me make a picture for you so that maybe becomes clear. So if I have a triangle A, B, C, and as you can see, what I'm saying here is that from A to B, from B to C, larger than or equal to A to C. So that's what triangle inequality says. And now what if I take it and express in terms of vectors? So then what I'm going to say, ABC, these are still ABC, and now I have vectors. So say this vector is AB, right? And this vector is BC. Okay? And the last one is naturally what's left is CA. Okay, so I certainly could use just the lengths of vectors to have it, so let me rewrite this. What I have, so the magnitude of AB plus the magnitude of BC is larger than or equal to magnitude of AC, or CA doesn't matter, or well, let's say AC. AC is better. The direction of the vector doesn't matter. Okay. What about the there is a better way to do it. What can you say about AC? Can you put AC differently?
The sum of A, B, and B.
That's right. That's right. This is AC, and it is actually equal to the sum of AB and BC, right? So AC is AB plus BC. Okay, and that allows me to write a formula that will be somewhat slightly different. So it will be, well, let's rename things. This is X, and this is Y, and this is X plus Y, right? So X plus X, the magnitude of X plus the magnitude of Y, larger than or equal to the magnitude of X plus Y. Okay? Okay? So, this is all applicable totally to multidimensional spaces. So the distances were introduced and were studied for n-dimensional spaces, and so do the properties of magnitudes apply to vectors of all directions. Okay. Okay. So the next, we continue on with geometry of vectors. So remember, so for points we know the distances. Okay. For vectors we know magnitudes, which is almost the same thing. What we are in that we were supposed to do it. I mentioned it before. It is angles. So the next topic is how to find angles between vectors. I did not actually. What I did not do, I did not write the magnitude formula for vectors. Let me do that. So to wrap this up, because it can be expressed certainly in terms of vectors. So if I have a vector A with components, say A1, A2, AN, its magnitude is simply the sum of squares and square root. A1 squared plus A2 squared plus so on plus AN squared square root. Okay, so it follows directly from our formula. It follows directly from the distance formula for points. Okay, so that works out. So that is a step one in geometry. Either left or right. So we can measure distances. So that's very nice. So the next one is how do we measure, or rather calculate? How do we calculate angles between vectors in terms of their components? So that is the question. So we just in the previous line we answered the question, how do we calculate magnitudes of vectors in terms of their components, and now we same question about the angles. So this is what we're talking about: vector A, vector B, and the angle we care about is this one. Okay, and so certainly what is inevitable, there will be some geometry involved in figuring out how to do it. We need geometry because it's after all a triangle, and the triangle with two known sides. And the angle is also, remember, if a vector is given, it means that the triangle is given. It means that the angle between them is given. So it is. We don't have to wonder whether it is determined or not. It is, because it's nothing about a triangle. The question is how do we do it in terms of the vectors, the components of the vectors. So we don't have to measure, nor we have to do any kind of geometry like high school geometry. You have a triangle, you have sides, and you want to figure out the angles, the missing side, and so on. So we want to do one nice formula. So once again, ideally, this is a formula like this that we want to have. One formula, and we have the angle, except we will have two vectors rather than one. Okay. So it turns out to be not too complicated, but we need an idea. And the idea comes from I suppose, dimension 1. I may have brought it up before, or maybe not. Okay, so dimension 1. Dimension 1, and we have two vectors, A and B. Notice that we do not care about magnitudes this time. So we intentionally separate the two things: directions, distances. So there might be distances without direction, or distances without direction, and directions without distances. So so as you can see, B is longer than A, but it doesn't matter. What's the angle? Is 0. Okay. So what else is? What are the possibilities?
-360 and 180 if it's on the other.
Right. Or, well, we're not going to be speaking in terms of degrees anymore. So pi, if B is directed in the points in the opposite direction. Okay, so I still have A here, and then I point B in the opposite direction. The length doesn't matter. Okay, so what if a length doesn't matter? In fact, let's try to do the let's suppose the vectors have unit length. Okay, so let me. Yeah, I'm out of time. Okay, so we'll just resume next week.